Welcome to the video lecture series on contact mechanics in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements at Luleå University of Technology. This is the second Fourier series part of the fourth video lecture on the application of Fourier techniques and multi-level multi-integration. This is the outline of this part, where we start with the continuous Fourier series and have a recap of that and how to compute the series coefficients, and then we move on to the discrete Fourier series and see how we can compute the coefficients there by means of the discrete Fourier transformation in MATLAB. So let us start by the continuous Fourier series. It's a key ingredient in lots of different signal processing, and here in tribology it's definitely worth mentioning in terms of representation of rough surfaces, for example. So we know that any function can be written in the following form, i.e. a Fourier series form, where we have a0 half plus this infinite series of an amplitudes times the cosine with the frequency omega n and x, and then we have the bn amplitudes for the sinusoids with the same frequency omega n, and this frequency is actually given by the discrete frequency representation n, in this way 2 pi n over L. Now of course there are restrictions, not any function can be written in this form, but if they are 1D, if they are bounded, if they are piecewise differentiable and periodic on the interval, the open interval 0 to L, so which is the periodic window. I've probably mentioned that a few times later on during this video lecture. So remember that the periodic window is that interval. Okay. So those coefficients, how to compute them then? If we have a function, how can we adapt a Fourier series to that function? We need to compute these coefficients. It turns out that the coefficients can be computed this way. So a0 is given by just 2 over L times integral from 0 to L of f of x dx. So L is the length of the periodic window. An is just nearly the same thing, but we add also the harmonic cosinus of omega n times x, and then integrate. And the b are very similar to the a. Yeah. How to compute these coefficients then? Okay. Let's first just make the problem dimensionless. So we view it in terms of this discrete frequency n instead of omega n. It simplifies things a little bit, not much, but it's cleaner. The proof will be cleaner on how to obtain the coefficients in this way. F of x being this Fourier series, and then we multiply it with cosinus mx and integrate from 0 to 2 pi. Well, this is simply put here, and if we consider the case when m equals 0, cosine mx is 1, and the integration is easily performed, at least for the first term. It's very, very easy. It's just to integrate 1 from 0 to 2 pi, and for the other terms we can switch the summation and the integration, and therefore we only have to integrate cosine nx or sine nx over the interval 0 to 2 pi, the periodic window. And this is simple since cosine is periodic, and no matter what the discrete frequency n is, its integral over the periodic window will always be 0, because the positive side cancels out the negative side. So it's 0. Same goes for the sinus, it's always 0. So that was easy. It gives us the result for the case where m is equal to 0. Just a0 times pi. Now the other part where m is greater or equal to 1 is a little bit more challenging, but not much, as we soon will see. So let's put it up here, and then we can immediately draw the conclusion that this one is 0, because sine and cosine, they don't mate very well. Doesn't matter the numbers, the discrete numbers of frequencies m and n, it will always be 0. The other one is a little bit more tricky, but not so much, and it turns out it's only non-negative and actually equal to exactly 1 when m is equal to n. So, summing up, in terms of the Kronecker delta function, we can write the result of this integral of the function times cos mx as a0 times pi when m is 0, and for m greater than or equal to 1 we have only an pi times the Kronecker delta. So actually it's always am, because Kronecker delta is only 1 when n is equal to m, and therefore an times Kronecker delta mn is am. I hope you heard the differences between my m and n. Otherwise, you can see it clearly on the whiteboard here, on the slide here. So, summing up, we can obtain a0 by integrating f of x from 0 to 2 pi, and we normalize this with 1 over pi. Same way, 1 over pi times the integral f of x times cos mx gives us am, the coefficients am. And of course, now when we switch back, insert into the Fourier series, we can interchange m and n, and then we have obtained precisely the series for the function fx. It's now your exercise to show that bm can be obtained in a similar manner. So moving now on towards the complex representation of the Fourier series will give us a benefit when we later on will look into the Fourier transformation. So let's do this. We, instead of representing now the function f of x in terms of cosines and sines, we use de Moivre's formula and represent it by a coefficient complex, coefficient capital AN times e to the power I n x. And here we will see later on, we will prove that a n is just the integral of 1 over 2 pi, 0 to 2 pi, and the function times e to the power I minus I n x. Sorry. Carrying on the same way as we did for the real Fourier series, we now multiply by a function e to the power minus I mx instead of sine and cosine of mx, and then integrate from 0 to 2 pi, the periodic window. So we can write this integral in terms of the series like this, and then we can switch the summation and the integral sign, and by the exponential rules or laws we can combine n and m in one exponential function like this, and of course this is just a cosine plus an I sine according to De Morey formula, and this formula is only interesting when n and m are equal, since if they were not, we could just say that we have cos for, let's say, k equals n minus m, and then we would have cosinus kx and I sinus kx, and we integrate those from 0 to 2 pi, they will be 0 all the time. And therefore we just have the result in terms of the Kronecker delta, which again, just spits out or produces am when applied to an like this. So we get the proof that we have an equal to 1 over 2 pi, and then the integral from 0 to 2 pi of the function, and times the exponential to the power of I to the power of minus I n x. And this is just the coefficients of the series. Okay, and now we realize there is a very clear relationship between the real and the complex series by, again, means of the De Morey formula, and therefore we can expand now that coefficient, that integral for the coefficient, and when we do, we get 3 different cases. First one here is listed for when n is less than 0, second one when n is 0, and third one when n is greater than 0. And if you carry out the computation here, I'm sure you all will end up with this relationship between capital AN up here and the lower letter AN and lower letter BN from the real Fourier series in this way. Now, when we know a lot of important things about the continuous Fourier series, it's time to look at the discrete version of it. In the discrete case, we evaluate the function f in the discrete nodes xj, and we define fjn as this value, as the value of the function at xj. Now, we note that xj is discretized and confined within the periodic window, and therefore we have j from 0 to n minus 2, so that it not actually ends up at the final node xl, because that's where the periodicity repeats itself. Now, and in this case, of course, there is a discrete Fourier series, and it looks like this, and it's actually nothing else but a truncated version of the continuous function. and the truncation takes place at n half. So instead of summing up all the harmonic components an cos omega n xj and bn sine omega n xj from n equal 1 to infinity, we sum them up from n equal 1 to n half. I have collected two links here where you can find a little bit more information about Fourier series, if you like, and in particular the problem with aliasing. So we need to calculate these discrete Fourier series coefficients, and it can be done in many ways, and what will follow next will be how to do this in MATLAB. So we have the series, we have x, xj equal j, delta x, where delta x is the step size, which is defined as L over the number of elements, and L is the length of the periodic window, of course, remember. J goes from 0 to n minus 2, and yeah, well, omega n is already included in the series above, so don't bother. So the coefficients A0, AN, and BN, they are computed by means of discrete Fourier transformation, which in MATLAB reads like this. So Fk is defined to be the discrete Fourier transformation of Fi with n nodes evaluated in discrete frequency k, which means that we need to sum Fn of xj times e to the power minus ixj, and then the discrete frequency or the frequency omega k, actually, from j equals 0 to n minus 2. But we note that the discrete frequencies k are going from 0 to n minus 1. So in combination with the Fourier transform, we can use the inverse discrete Fourier transform to transform back the data to the data that we had, and this is done exactly in this way in MATLAB, where we see the normalization, which is specific for MATLAB and may differ in other in other programs and other ways of computing it. The 1 over n may be 1 over square root of n here and 1 over square root of n in the Fourier transformation, for example. But by means of this sum, we can get back the function fjn, the values of the function f in xj, which we just transformed into fk with n discrete nodes. It turns out there is a quite clear relation between the discrete Fourier transform and the complex Fourier series. And this can be seen as a continuous representation of the inverse discrete Fourier, which mathematically can be described like this. So here in green we have the continuous representation of the inverse discrete Fourier transform, where we just have replaced xj with x. Now, the continuous form of this inverse discrete Fourier transform in green actually resembles the continuous Fourier series quite a lot. Can you see the resemblance? I'm sure you can. There is a factor 1 over n in front of it, and of course that the continuous Fourier series, it goes from minus infinity to infinity. So this suggests that we can apply the same strategy to derive the coefficients, which is very nice. And here you see the exact way of doing that. And the only thing we have to think of a little bit is that we now consider not the dimensionless formulation. So we integrate from 0 to 2 pi, but we integrate from 0 to L. But all in all, we can easily derive the coefficients, which are now called Fk, for this discrete Fourier transform. Moreover, there is also a clear relation between the coefficients of the DFT and the complex formulation of the Fourier series. So indeed, the coefficients Fk of the discrete Fourier transform are given by this expression in terms of e to the power minus I 2 pi k over L x, but the Moivre formula tells us that this is just cosine and minus I sine, and therefore we can just evaluate it again in this way, and for k equals 0 we have a nod times a constant, and for k greater than 0, for 1 and greater or equal to 1, we have ak minus ibk, which means that we can formulate a node as 2f node over n. So given the discrete Fourier transform, we have Fk, and in particular we have f node. By f node we get a node. Okay, so we have the first important part of the Fourier series. And then next we have the real part, which is just ak, the real part of the coefficients of the discrete Fourier transform. Well, times 2 divided by n gives ak. And the negative imaginary part of 2 times the Fourier coefficient over n gives us bk. So Then we construct the real discrete Fourier series by first taking the discrete Fourier transform using the fast Fourier transform technique in MATLAB of f to get capital F, which is the Fourier transform now. And this is actually a 1 times n vector also. So next step is to construct the frequencies by means of the discrete wave numbers, and this may be done like this. Now you have to remember that k here is just the positive part of the frequencies of the frequency response. So we have k are frequencies from 1 to n over 2, but we also transpose this one for later on. It will be better if we have k represented as a column vector than a row vector for the subsequent operations that we will perform. In this way we construct omega. It will also be an n half times 1 vector. Now we can evaluate a node by just taking the first value of f times 2 and divide it by n, and following the rest of the recipe that we presented before, we get all of the n's by just taking the real part of the rest of the frequency, the rest of the Fourier transforms for the rest of the discrete frequencies, and b as the negative imaginary part of the same thing. So now we have a and b, they are actually 1 by n over half vectors, and in this way we have made it very simple to write the Fourier series like this. So we have an implicit summation in the matrix vector multiplication that we see on this row, and we can figure that out by considering the size of these constituents. So we have a is a 1 by n half vector, we have omega is an n half times 1 vector, x is a 1 by n vector, so we can clearly multiply omega and n, and when we multiply omega by n we get an n half times n matrix. So it remains to visualize this, and here you see a command which visualizes two functions at the same time. So we have the function in black, and we have the original function in black, and the Fourier series representation of the function in red with a dashed dot line to really show the differences and the similarities between the two. And we also take some time to evaluate the error or the differences between these two representations. So we measure the absolute value of the Fourier series representation and f, and then we sum this, we divide or normalize by the absolute value of the f's, and we get a normalized error. Graphically, the Fourier series, or the function in black and the Fourier series, they overlap. So we really need this error measure to see that there is a numerical discrepancy between them, which is larger than the machine error of the system. The machine error of the system is about 2e minus 16. Sorry, 10e minus 16. So this is clearly not numerically exact. There is an error, or there is a difference between the Fourier series representation and the function representation, and that comes from that we added this non-harmonic content. If we had kept only the first pure sinusoidal part, i.e. the sine 4 times w times x part, that would be numerically exact. And it would have been numerically exact all the way up to n½ minus 1 for the frequency that we just represented by this 4. You can try that, elaborate on that yourself. At this point, we know pretty much exactly how to obtain the discrete Fourier series, and we know how we can make use of the Fourier transform, the discrete Fourier transform, to obtain A0, AN, and BN in the cosine sine representation that we have been treating so far. Now, by means of simple trigonometric relations and other mathematical relationships, we can transform this expression into an alternative form, which sometimes can be more convenient to use. And this, there are many alternative forms. This is one of them, and it's represented here by one cosinusoidal function and a shift phi n, as you can see. Now, there is of course a relationship here between the Cn and the An and Bn, and also C node and A node, and then we have this relationship that defines the phase shift phi n, which is just negative of Bn over An, and the tangent of that. And here we have following MATLAB code that actually creates this alternative representation of the Fourier series. And if we visualize it, visualize, it will be of course the same thing.